Okay, so let's have a look at this problem then. So this is the actual solution for this particular problem here that we're going to arrive at. It's a complex solution. We're going to look at how we arrive at this value for n that has a real part and an imaginary part. The complex solution, remember, is given because of this imaginary number j, the square root of minus 1 as a reminder. So let's see how this works. Well, if we look at the differential equation here, then if I were to form the auxiliary, I'd have 1m squared, so a is 1 in this case, b is 6, and c equals 13. So a equals 1, b equals 6, and c equals 13. And I plug them into the quadratic formula, and I end up with, here, a negative root, because we've got minus 1 times 16, or minus 16 is our solution. If you work out this particular part of the quadratic equation, you get minus 16, so it's a negative root. So do you remember what we do in this case? We split it. Negative 16 can be minus 1 times 16, so we can call that the square root of minus 1 times the square root of 16. And the square root of minus 1 is j, so square root of 16 is 4, so we end up with 4j here. So we get minus 6 plus or minus 4j over 2. Just pause while you just check your understanding as far as there. That's the complex numbers bit. The fact that the square root of minus 1 can be called j, the imaginary number. So this part becomes 4j. That's the important thing to see.
So we saw that.
So we end up with this as our solution, and minus 6 over 2 is minus 3, and 4j over 2 is plus or minus 2j. So that's where this solution comes from, minus 3 plus or minus 2j. So if we look at the general solution that you're given on the sheet, then we can see that the solution has the form. Just need to pause and have a look at. So if we look at our table results, we now have a complex solution here. So it's this. We've got a negative root of the form alpha plus or minus beta j. So alpha and beta are used, alpha plus or minus beta j. So beta in this case is beta in this case is the 2j, and alpha is the minus 3. So we look at the general solution here. And so what is alpha? Alpha is the number that goes as the coefficient of x in the exponential part of this, and beta is the angular velocity, or the constant in the cosine and sine terms here. And so we now know what alpha and beta are, and we can write the general solution, which is here. So we know that alpha is minus 3 and beta is 2. Here. But we've got to find A and B. So there's our general solution. It's not the particular solution because we don't know A and B. So we've now got to find A and B. And to find A and B, we have to put in the initial conditions. So if we look at the original equation, we know that when x equals 0 in this case, y equals 3 in the differential side. So similar sort of problem that we've looked at before, but we've got to differentiate this thing before we can put the dy by dx in. And again, if you look at it, we've got one function multiplied by another function, so we get 1 equal u and 2 equal v, and use the product rule again. So the product rule is generally what we have to use in these sorts of problems. So we write down u equals e to the minus 3x and differentiate that to get this. V equals this. The differential of cos is minus sine, and the 2 comes out, so that gives us this as a reminder. The differential of sine is cos, so the sine turns to cosine, the 2 comes out again and goes in front. So that's the differential of u and the differential of v. So then we plug them into this product rule, and we get this. looks pretty complicated, but it's just u, the first term, multiplied by the differential of v, plus v multiplied by the differential of u. And then we tidy up, because e to the minus 3x is common to both. We can take that outside the bracket, and we're just left with this term underneath. So just pause and have a look and see if you can see that algebra that gets you to there. Okay. The only awkward bit may be that once we've taken this e to the minus 3x outside here, where does this minus 3 come from? That minus 3 there that goes in front here. So I'll put that there, and that comes down here. So now we've put in our initial conditions, the boundary conditions. When x equals 0, y equals 3. So if I put x equal to 0 into the original equation, x equals to 0 into here, then that becomes 1. And if x equals to 0, then the cos of 0 is 1, and the sine of 0 is 0. So that's disappeared, and we're just left with the a term. Cos of 0 is 1, that becomes 1. So we just left with a equals whatever y is, which is 3. So a equals 3 is in our boundary conditions. A equals 3. As explained here, look. 3 equals 1. Cos of 0 is 1. Sine of 0 is 0. And then the second initial condition we put in, when x equals 0, the differential is 7. So again, putting those values in, the differential is 7. Again, if the x is 0, quite a lot of it simplifies. Sine of 0 is 0, so that's gone. Cos of 0 is 1, so that just becomes 1. So it simply flies right down to this. But again, we know that a is 3, so it's quite straightforward to find out what b is, and b is 8. So we don't have to solve any simultaneous equations here, it's just a case of simplifying it and remembering that the cosine of 0 is 1 and the sine of 0 is 0. Or, on the calculator, I'm not sure. So then we can write down what our particular solution is here. You could plot that on an autograph and see what it looked like, and that would be the solution. And that's about the most complicated form that you're going to get in the exam, where you might have a complex solution like this.